This is section 15.4, the chain rule. The chain rule is the most powerful rule that we have to take the derivatives of functions of single variables. We use it all the time in Calculus 1 and Calculus 2, and we've even been using it in the last couple sections where we're taking derivatives of functions, like more complicated functions. The chain rule gets a little bit more complicated when we start dealing with functions of multiple variables, like ones where the input is a point in the plane, or ones where the input is a point in space. So the plan here is we want to try to figure out what the different forms of the chain rule are when we're dealing with functions of multiple variables. We need those because we're going to be taking a lot of partial derivatives now that the last section covered partial derivatives. The first application we'll have of how to use the chain rule is we'll apply the chain rule to particle motion problems. So first, let's think back to the chain rule in Calculus 1, figure out how it worked, and then we'll rethink about it in a different way that will generalize better in Calculus 3. So the way that this was usually introduced, and the way that we usually think about the chain rule from like the regular old single variable chain rule, is you imagine, well, what if you have an outside function and an inside function? If you have an outside function and an inside function, and you want to take the derivative, you do like the derivative of the outside function, leaving the inside alone, and multiply by the derivative of the inside function. That's fine, and that works totally, like it's totally acceptable. But it doesn't generalize very well. We're going to have like inputs of multiple variables, and those multiple variables might have several insides. Like we don't want to think about outside and inside as much. Instead, we will rephrase it this way. So this is just the same chain rule but phrased a different way. It says, instead, say you have your variable y, and it is a function, but that inside the input to that function depends on another variable. It's also a function. Here, it's the exact same thing. F is the outside function and g is the inside function, but we've given this intermediary a name, u. If you do that, if you say, oh, okay, we'll say that y depends on u, and u depends on x, and we're trying to find the derivative of y with respect to x, then you get a nicer looking form of the chain rule. And you probably saw this at least once in your Calculus 1 or 2 classes, this way of writing the chain rule. Let me just show you what the schematic diagram is that we'll use to build this kind of formula. So in this situation where y depends on u, you would say, you'd put y on top and say, put a vertical line down to u, meaning y is a function of u. And then u is a function of x. In the situation where you want to find the derivative of this top variable with respect to the bottom variable, you'd say, well, that path goes through u. So you'll say dy dx is dy du times du dx. I want to warn you that although it looks like these are fractions and that the du's cancel, we finally get to see the reason right now in this section why you don't actually do that, why you don't cancel du's and think of these things as fractions. It like mostly worked for a long time, but it's not going to work anymore. So let's get into a multivariable function and just see what happens. Okay, so here instead of a function with an input of one variable and the output of a number, instead the input is two variables, like a point in the plane, and the output is the height. In this case, we have z depending on x and y, and then x depends on time, and y also depends on time. In this case, z depends on time two different ways. Z depends on time through x and through y. And in this situation, what the chain rule of several variables tells us is that dz dt is, well, you kind of do the chain rule for each of the paths on this dependency diagram. So you want dz dt. Well, z can get to t through x. So here's dz dx times dx dt. And z can get to t through y. So here's dz dy times dy dt. Well, what do I do with these? We add them together. this is the first case of the multivariable chain rule, and this diagram is the best way to build the correct expression for all these cases. But the main thing I want you to notice is that you can't cancel the dx's and cancel the dy's, because then you would get like two copies of dz dt. This is finally the reason why you can't cancel all those things, like why it doesn't work every time. So this looks kind of crazy, but let's do an example. So this first example says that z is sine of xy, but x is changing with time and y is changing with time. If x and y are both changing, then z will also be changing. And the question we can ask is like, okay, what's dz dt? Let's use the chain rule first, because we want to see one example of it at least. But then there's another way to do this particular problem. So to do the chain rule, I recommend that you draw this like dependency chart. Say, okay, my z depends on x and y. X is a function of t, and y is a function of t. So dz dt, that is not a t, dz dt has two components, the component through x and the component through y. You'll notice that what I wrote here is a little bit different from what I wrote above, and that's because the thing I wrote above is wrong. If your function depends on multiple variables, like our function z up here, this function z depended on x and y. So you can't really do dz dx. That doesn't really make sense. If you want the derivative with respect to x, you need to say, oh, I'm doing a partial derivative with respect to x. Or here, I'll find the partial derivative with respect to y. dx dt is fine because this function x only depended on time. It didn't have other inputs. But for this function that has two inputs, saying dz dx is just crazy. Instead, you write partial z partial x and partial z partial y. Okay, I've got it written correctly down here in the example. Anyway, let's find these things. So partial z partial x is, let's take the derivative of sine xy. We are taking the partial derivative with respect to x, so we're thinking of y as a constant. So when I take the derivative of sine xy, the inside function is xy, and the derivative of xy is y. So this is partial z partial x. Then I have to find dx dt, but I have this equation that tells me what x is in terms of t. So I'll take the derivative of x with respect to t. This is the first path. This is partial z partial x times dx dt. Then I need to go the other route. So first I'll find partial z partial y. This time when I take the derivative of xy, the result is going to be x, because I'm thinking of x as the constant here. Then when I multiply by dy dt comes from this equation. The derivative of an exponential is itself times the derivative of the inside function. So in total, what do I have? It looks like I have a cosine xy that I can factor out. And then the first term is going to have 5y e to the 5t. And the second term has a negative 3x e to the minus 3t. Now, this is correct, but it's a little bit odd to leave it like this. This answer has x's, y's, and t's in it, and that should feel a little bit strange, because if I needed to, I could write x in terms of t, and I could write y in terms of t. So we look back at the problem when we have a weird-looking answer like this to see if the problem gives us any way out. Like, for example, the problem might say, write everything in terms of t, or get all the t's out of the answer, Or in this case, it says find dz dt at t equals 0. Okay, well, when t is 0, we can plug t into all these other functions to see what everything else equals. When t is 0, if I plug that into my e to the 5t, I get that x is 1. And when t is 0, I also get that y is 1. So I can plug all these things in. Cosine 1? Okay. Okay. Here's 5 times 1 times 1 minus 3 times 1 times 1. So I get 2 cosine of 1 radian. Great. So that's how the chain rule is applied. You draw the dependency chart, follow all the paths from what you're starting with down to what you are taking the derivative with respect to, add up all of those components. Then watch out for how your answer looks, because if your answer looks incredibly strange, you should go back and make sure that you're actually answering the question. Okay, so that's one way to do it. That's the way to do it with the chain rule. We also want to do it this one. Like, the functions are not too complicated, so you can actually do this one without the chain rule. It's asking for dz dt, and z is sine of xy. So to find dz dt, you could instead just say, well, there's no t's in here. I want everything in terms of t before I do any work at all. So sure, go for it. X is e to the 5t, and y is e to the minus 3t. When I multiply these together, I get to add the exponents. So z is actually sine of e to the 2t. And now I can just find dz dt directly. dz dt is cosine of e to the 2t times the derivative of e to the 2t. And if I finish this up by plugging in t equals 0, then I'll get cosine of 1 times 1 times 2. So I end up with 2 cosine of 1. Get some orange juice here. Some tasty green screen orange juice there. So I think when you look at this, your reaction should be, thanks for the chain rule, but no thanks, I'm never using that. I like the other way better. I like the way without the chain rule. It was great. Please leave me alone and don't make me deal with the chain rule ever. This is just how this always works when you get a more powerful tool, is that if you use it in easy situations, an easier method is better. So if it's possible to escape using the chain rule, you escape it, the same way that you have always escaped using complicated rules whenever it was possible. Like, if you want to get out of the quotient rule, you can try to find a way out of it. Here, if you can get out of using the chain rule, then go ahead. Nobody will judge you. Like, you should totally do this way. Okay, let's look at some more. So in this example, I've got z in terms of x and y, but I have x and y in terms of some other variable. And the question is asking to find dz d theta, the derivative of z with respect to this variable that's like two layers deep. I like to just organize myself. There's no requirement to draw this diagram, but I don't know. Z depends on x and y, x depends on theta, y depends on theta. So here's my nice diagram. Now I can find dz d theta by following this path. Anytime you have a branching path, those are partial derivatives. So I'll find partial z, partial x. And then any non-branching path is a regular old derivative, dx d theta. And then partial z, partial y. dy d theta. Then you can just find all these things. So partial z partial x is the derivative here where x is the only variable. That's 2x. Dx d theta is minus sine theta. Partial z partial y, that's 2y. And dy d theta is cosine theta. Now it says find dz d theta and simplify your answer in terms of theta. That's your clue that, like, indeed this, well, hopefully this answer feels bad to you. Like, this feels like it shouldn't be a final answer. It's got way too many different kinds of variables in it, and maybe something would go well if we simplified it. Hopefully the question will tell you how to simplify it. And indeed this one says, put everything in terms of theta. So I substitute x equals cosine theta. This first term will now be minus 2 cosine theta sine theta. And substitute that y is sine theta. So I get plus 2 sine theta cosine theta. And those cancel. So dz d theta was 0. Great. What? Why? Like, this doesn't look like a constant to me, right? Like, I had a function, I took its derivative with respect to a variable it depended on, and I got 0. That means that z is actually a constant when theta, with respect to theta. How's that possible? Oh, we've got... Why does this make sense with 3 question marks down here? Okay. Why does it make sense? Okay. I wanna give an algebraic reason before we do the geometric reason. The algebraic reason is, well, how could x squared plus y squared actually equal a constant? And the reason that happened is that x is cosine theta and y is sine theta. So z is actually 1. So yeah, if z is just a constant, then when I take dz d theta, I'm going to get 0. I'll put this in parentheses or something. The text here tells me that it might be smart to check out a geometric or a graphical reason for this. And, well, the reason for this is that z equals x squared plus y squared. Z equals x squared plus y squared is a surface. And at each level, if we drew the level curves, like say at z equals 4, or z equals 1, at each level I get circles. So z equals x squared plus y squared is a shape that's made of circles. Let's see if I can get a reasonable picture of this. I wonder if the contour lines would have been better. No, not really. Oh well. To figure out like whether, so the question when your cross sections are all circles is like, okay, are the circles getting bigger in a constant rate so that I have a cone? Or are the circles like do they get bigger faster at the beginning and then like peter out so that I have like a paraboloid? And the easiest way to see that is to just try like x equals 0. When x equals 0, I get z equals y squared. So I'll get this shape. And then try y equals 0. When y equals 0, I get that z equals x squared. So I get this shape. So in fact, z equals x squared plus y squared is this paraboloid. And x equals cosine theta, y equals sine theta. That's a unit circle. So I'm going to be like slicing this paraboloid with a cylinder. that's just at radius 1. The slice will just be a circle up here. It's the unit circle, but up at z equals 1. Now, if theta changes, we go around the circle, but z doesn't change. So if theta's changing, z isn't changing, that's dz d theta equals 0. I don't really like this reason as much as I like the algebra reason. The algebra reason is so satisfying to me, like Pythagorean identity. Ta-da! But if you like the graphical reason, that's okay too. Okay, let's try to write down another case. In this case, we'll say, hey, what if f depends on like n variables, like any number? Maybe n is 10, or maybe n is 8, or n is 2 or 3, that would work too. And all those x's, all those variables that z depends on, all depend on time. Then what would happen? Okay, well, the dependency diagram would say z depends on x1 and x2 and a whole bunch of things, and also at the end xn. And then each x, xi, so all the x's depend on time. Well, you do the same thing we did with the multiple dependencies earlier. You deal with them each separately and then add together the results. The first one is a branching path, so I need partial derivatives. So partial z, partial x1. And then x1 only depended on t, so I write dx1 dt. Then plus the second path here. The second path is partial z, partial x2, and then dx2 dt. And then there's a whole bunch more. And then we'll write the last one. The last one goes through xn and then to t. So it's partial z, partial xn, dxn dt. So it doesn't really matter how many variables z depends on. You draw out the little diagram of what variables depend on what variables. And then if you want dz dt, then you look for all the paths that go from z to t. Like what is in between. For each one, you make one of these little contraptions. It's kind of nice. Let me pull up. I think I wanted to say something else specific here. Nope, it's just that picture. Okay, next page. Okay, so let's say that we have these two particles. So we're getting onto the second objective here, where we're trying to use the chain rule on particles, on particle motion. We've got two particles that are traveling in paths that come from these parametric equations. So particle 1 has x is cosine t and y is sine t. This is going around in a circle. And particle 2 has x is 2 cosine 3t and y is sine of 2t. And I do not know what shape that is. Yeah, I have no idea. So let's go through these questions about these paths. Not all of them will require calculus. Some of them will. We'll try to use calculus only when it's necessary and use the chain rule only when it's necessary. So first it asks, how far apart are they? That's just going to be a distance formula. When t equals pi over 2. Okay, well, when t equals pi over 2, x1 is cosine of pi over 2, that's 0. And y1 is sine of pi over 2, which is 1. x2 is 2 cosine of 3 pi over 2, that's 0. And y2 is sine of pi, which is 0. So at this time, particle 1 is at 0, 1. And particle 2 is at 0, 0. And that distance is 1. It wants us to assume feet, So we'll say how far apart are they, and that's 1 foot. Then we want how far apart are they at any value of t. Okay, well now we'll just use the distance formula. We'll take the square root of, just write down what the distance formula says. So it's the difference of the x's squared plus the difference of the y's squared. Now, this is where this can go really wrong for you if you misunderstand the purpose of the question. In general, no one wants you to do a huge amount of crazy algebra and trigonometry unless there's a purpose to it. So if you've been trained all your life to like simplify everything forever or it's wrong, that's kind of counterproductive, because it's actually really useful to leave x1, x2, y1, and y2 alone here and just say, yeah, they all depend on time, but like it would be useless for me to put like 2 cosine 3t in here when 2 cosine 3t already has a perfectly respectable name. It's named x2. Until we get a reason to like put all that stuff in, we should just leave it like this. Just so that I don't have to scroll up and down all the time. I think I will copy them down. So x1 is cosine t, y1 is sine t, x2 is 2 cosine 3t, and y2 is sine of 2t. Okay, now let's find how fast the distance between the two particles is changing. How fast it's changing is the derivative. So we're going to find the derivative with respect to time of the distance. Okay, well, this is a huge, crazy like function. This is a big function that depends on x1, x2, y1, and y2. Well, here's what that dependency diagram looks like. Distance depends on x1 and x2 and y1 and y2. And all of those depend on time. Now you could substitute them all in, square everything, and hope that something really good happens. Or you could just use the chain rule. And the chain rule kind of like breaks everything up into individual pieces so that you don't have to deal with the whole giant disaster all at the same time. So the derivative of distance with respect to time will be, well, we're going to need partial z partial x1 dx1 dt plus partial z partial x2 dx2 dt. And just each path from the distance to t is getting its own term. Partial z partial y1 dy1 dt, and partial z partial y2 dy2 dt. And then we can just find each of these. Okay, I'm going to have to take the derivative of z with respect to x1, and the derivative of z with respect to x2, and the derivative of z with respect to y1. I'm going to have to write this thing a whole bunch of times. I don't really want to do that. So let's just give it a name. Anything that you think you might have to write all the time, just give it a name first. So we'll say how about the inside of this? Let's just call it a. Let a be x1 minus x2 squared plus y1 minus y2 squared. Just so that I don't have to write it over and over. Now when we do dz, or partial z partial x1, Well, it's half of a to the minus a half. And then I need to finish up the chain rule. So that's multiplied by the derivative of the inside. But the derivative of the inside has a bunch of stuff that's all constants. The only part of this that's a variable in this perspective is the x1. So the derivative of the inside here is 2 times x1 minus x2. So this part is partial z partial x1. Now I need dx1 dt. Well, dx1 dt is minus sine t. That's our first term. Now let's do a second term. Partial z partial x2. Well, same deal. It's going to have half a to the minus a half, but then multiplied by the derivative of the inside. If since x2 is the variable here, the derivative of the inside here is almost exactly the same. It's 2x1 minus x2. But times the derivative of the inside has another minus 1. Then I need dx2 dt. dx2 dt is kind of a mess. I get minus 2 sine 3t times 3. Okay, let's just do the other terms. So we'll go with the y1 term. Again, I'll have 1/2 a to the minus 1/2. But then now the derivative of the inside is using this term. So I'm going to have 2 y1 minus y2. Then dy1 dt. And dy1 dt is cosine t. Finally, let's do the last one. Partial z partial y2. Same kind of issues. Again, because now our variable is the minus y2, we'll have an extra minus 1 here. Then we need dy2 dt. dy2 dt is cosine 2t times 2. Okay, this is a huge mess, and it has a billion variables in it. It has a, y1, y2, x1, x2, t, it has everything. So we could try to simplify it, but you should not do that if you can avoid it. Instead, this says to plug in t equals pi over 2. And when t is pi over 2, a is, t is pi over 2. When t is pi over 2, what we did in part A was find that the distance is 1. So that means that a is 1. Also, we know all these values of x1, x2, y1, and y2. They're all 0 except y1 is 1. Get out of the way of my own writing here. I'm really worried that people will get to this and say, oh my gosh, this is insane. This problem is so hard. It has so much algebra. And then like start doing a bunch of algebra. When actually, no, the part that was tricky was the calculus, doing the chain rule. And then as soon as you're about to do the algebra, you should say, oh my gosh, I don't want to do this algebra. Let's find a way out. And the way out is, oh, it tells us t, so I don't have to do any algebra. Now I can just substitute in every single thing. So I'll have 1/2 times 2 times x1 minus x2 is 0 times minus 1. Okay, well that term is 0. Then I have 1/2 times 1 times 2. Ooh, this term's also 0, the pink term here. Don't care what the rest of it is because that term is 0. The third term has 1/2 times 1 times 2. y1 minus y2 is actually 1, but cosine pi over 2 is 0. Okay, and then 1/2 times 1 times 2 times 1 times minus 1. Cosine of 2 times pi over 2. cosine of pi is -1. So we actually just get one of these terms that actually contributes anything. The 2's cancel, the minuses cancel, and it looks like I have 1 times 1 times 1 times 2. So the answer is 2. Because we were supposed to assume that it was feet and seconds, this is how fast a distance is changing, then we write this as 2 feet per second. This problem was complicated, but the chain rule made it easier. The chain rule took a huge disaster with 1,000,000 variables and said, don't worry about it, deal with all the little paths to all the different variables separately, and then don't simplify anything at all. You never need, I can't say you never need to, but like you generally have no reason to do that unless someone gives you a reason. And then like most of the terms are 0 and everything's great. Yeah. Okay. Let's get one more mode for the chain rule. Again, we're going to follow the same plan, which is you just draw a dependency diagram and then follow all the paths you can to where you're headed. So here's our new complicated form. It's like, okay, z depends on x and y like before. But what if x now depends on s and t? And y also depends on s and t. Now, to find dz ds, well, I don't know, there's like a bunch of ways to go. And the trick is that it's just not that big of a deal. As long as you have this dependency chart, you say, well, if you want dz ds, you find all the paths from z to s and get a term for each of those. First one is from z to x to s. Both of these moves are branching paths, so we get partial derivatives for both. So I have partial z, partial x, partial x, partial s. That's the first path from z to s. The other path from z to s goes through y. So that one is partial z, partial y, partial y, partial s. Looks the same as what we had before, except there's more partials and less d's because, well, everything was branching here. Similarly, there's two ways from z to t. So dz dt is partial z, partial x, partial t, plus partial z, partial y, partial t. Let's see it in action. I think there's only one of these examples. Oh, what is this? Okay, we're not actually going to write out this case, but the point is, like, suppose that lots of things depended on lots of other things. It's all the same. You just draw this diagram and you follow all the paths from like the thing you're starting with to the thing that you're aiming at. So I think this is actually a joke in the notes, but whatever. We'll do one example to see how it works, and then we'll call it a day on this section. So let's say z looks like this. When someone is asking me to find partial z, partial s, then I'm going to try to figure out how I can get from z to s. It looks like z depends on x and y initially. And then x depends on s and t. And y also depends on s and t. So to find partial z, partial x, did I say x? To find partial z, partial s, which is the question, well, there's two paths from z to s. One of them goes through x, and the other one goes through y. In the first example of the chain rule we did, it seemed like you could basically always get out of doing the chain rule by just substituting everything in. I'm going to take another drink here, and you should imagine what it would look like if we substituted that x and that y in for all those variables in z. Yeah, I'm not doing it. So let's find partial z, partial x. Partial z, partial x is, okay, derivative of x squared is 2x, and y squared is a constant. So here's 2x y squared. Derivative of y cubed x is y cubed. So here's partial z, partial x. Then partial x, partial s. Well, I've got a constant, sine t, and the derivative of s squared is 2s. So 2s sine t. So that's partial z, partial x, partial x, partial s. Then we need partial z, partial y. There's partial z, partial y, and partial y, partial s. T cubed is a constant. Derivative of cosine s with respect to s is minus sine s. Let's get the minus in here somewhere. Maybe like here. So this is partial z, partial s. I got all the pieces, right? Zx, xs, zy, ys. Okay, this is a mess. I don't want to circle this. And in fact, the problem tells us to get everything in terms of s and t. So we can do that. That means any x's and y's should not be in the final answer. Can I factor anything out? No? Maybe like 1y? Ugh. Oh well. Okay, 2xy squared. So I'll have a 2. X. Yeah, this is just ridiculous and ugly. That's just how it's going to be. So 2x y squared plus y cubed times 2s sine t. Minus, okay, 2x squared y plus 3xy squared times t cubed sine s. Yeah, great, whatever. Okay, it's a disaster. Nothing good happens. It's not even anything to factor out. Oh well. Okay, but this answer is ridiculous, and we would get the ridiculous answer if we did it the other way too, where we like substituted in x and y and took the derivative with respect to s. But we had to do almost no product rules when we did it this way. By doing the chain rule like separated out all the products nicely, and we did them all individually, and we just had a couple of algebra obnoxiousness to do, and like actually writing the answer was a little annoying. But the chain rule saved us from all the actual hard work. Okay, so that's the chain rule. Draw the little diagrams, keep track of all the variables, and see what is the goal. If your goal is to get from z to s, then you find all the paths from z to s and build a term for each of those and add them together. The reason you might possibly want to do this is if you've got some particles moving around and the particles are made of vector valued functions or parametric equations, which like is usually what's going to happen. That means there's a whole bunch of variables floating around, and the chain rule might protect you from having to think about them all at the same time. So if it's appropriate to draw this diagram because you have your master variable that's dependent on a lot of intermediate variables, that's when the chain rule is going to be useful. Okay, that's it.